quotient rule, right? Why is calculus getting more complicated? In my short answer is the product rule. That's it. The product rule makes everything so complicated in the higher mathematics. So here you begin to witness what it is. So I'll give you some time, a lot longer than usual, to write this one down and really imprint on the corner of your brain. And never forget with the clause I usually throw until you die. You know, you should not forget this one. It's this mathematical nature, mathematical description of could be some part of a nature. It's not some rule in mathematics. It is tied to the way things work in the world. Okay, f and g are differentiable function, whatever that means. Usual expression we're dealing with, those are all differentiable. And f times g, right? F plus g, that was easy, right? X plus sine x, no one had difficulty of what the derivative of that one was, right? Because of what fancy word that describes this property? Derivative of x plus sine x was easy because of what property of a differential operator? One word. Linearity. Linearity allows you to do that, allows you to do that. Boom, piece of cake, right? Product rule, it is not part of linearity. You cannot do that anymore, right? New rule. Don't touch the first factor and differentiate the second factor. Don't touch the second factor, differentiate the first factor. For some reason in my brain, it works like this. This is how I learned. And then until I die, it's going to be like this to me. But you know it's the same thing, right? 3 plus 4 is 4 plus 4 plus 3. Messed up. All right. So differential operator goes like that. Fair enough? All right. You see some symmetry. Is that easy to remember? Not too bad, right? Yeah. So we're gonna have that right up there, and we're gonna witness this interesting moment. You all know the answer to this question, right? Okay. What do you think I'm gonna do? It's a fun part of a mathematics. Mathematics, there's no anomaly. You go this route, you go that route, your answer is always the same, right? So do you see how to apply the product rule to this guy? D dx. You have to write the product of two things. Some idea? X times x, right? So if you go through that, you're supposed to get what answer? You know the answer already, right? What is the answer to x squared? 2 times x, right? So do you think you can apply that? That looks like a good exercise, right? So I'm going to apply the product rule to that one on here. Exercise number 1. PR, product rule. All right, was that okay? I go exactly by what it's written, but soon it'll change because, you know, that's not how I remember this one. But that's the same thing. X times x, nothing happens. X is this f of x, right? And g of x is that x. So if you differentiate that one, it becomes 1, and vice versa. So 2 times x. We verified that, right? Fair enough? The following is called inductive reasoning. So you build on top of it. Now we have this new fact, x squared is 2x, right? Have that in you. So this is in our bank of knowledge now, and we have a product rule. Can we go to the next step? What is our next step? Apply product rule, right? And exercise number 1, right? To compute what? ddx of, anybody? X to the third. Thank you. X to the third. So what should we do? You have to split the x to the third into product of two functions, right? Okay? In non-trivial way. Don't do that 1 times x to the third. Something actually. Split it and then apply the product rule. And if you have to, use this rule we just constructed. X squared, derivative of x squared is 2 times x. All right, was that okay? All right, so I'll leave the rest of the part, intuition. So if you keep building on that, you will verify that rule. What was the rule that we're witnessing here? X to the n is n times x to the n minus 1 is built on top of each other like that, right? This is called inductive calculation. You built on top of what we had just is we go next one and next one like that. All right, fair enough. That's what the product rule. You don't have to now go and do the limit h approach to 0 to explain x to the third. You just have to explain what the product rule, why the product rule is true, right? Which we'll do that. I find it is, like I said, this is the important rule in this whole derivative business. So we need to understand that, why that one looks like that. But for now, we just have to memorize and be able to apply it. So that's what we are practicing. All right, here it is. Peak practicing that one. Use the product rule to compute the derivative of this guy in here. Okay. That's our exercise number 3 up to here. Then after that, we're going to check our answer, and then we'll do evaluate the derivative at pi over 2 later. Okay. So let's work on the derivative part. Exercise number 3, use the product rule. If possible, don't look at the rule. All right. We practiced already like a couple times. Use your calculator and fold it up, hide the rule, and see if you can apply it in your mind directly. If well, I'll show it here. All right, how was it? Or let me explain how I wrote it down. First, this is my f of x and this is my g of x, right? Don't look at, I know it sometimes happens. If you look at a sine x, this is not your f and g. Sine x is one function, right? So don't look at it as a sine as a product. The product rule applies only to product. So this is not that. So this is a function f of x. This is a function g of x. They wrote f prime of x and g of x. And I'm again begin to do differentiating first one first. So it doesn't matter. Instead of writing that f prime of x, none of this one is actually called f of x and g of x. So this is a useful notation, especially when you're doing theoretically, especially when you cannot differentiate this one, but you want to apply the product rule. Then what are you going to write that down? You're going to write down ddx of that thing that you cannot differentiate at the moment, right? So it's very useful notation. It's a good idea to get used to this abstract step. Here I didn't really differentiate it, right? I wrote it down 5 times x squared and derivative. That place right here is supposed to be the derivative of 5 of x squared alone. Then I wrote it down and move on. So this is notable skill, notable thing to use in there, right? Just in case if you can't do it. This one's easy, so I would do probably just cosine x. But this place here is supposed to be the derivative of 5 of x squared, 5 times x squared. This is denoted like this. Then I thought about also what is a derivative of 5x squared? Constant multiple rule allows you to go outside and differentiate x squared, so it's a 2 times x, right? So I know now that has to be 10 times x, things like that. So that's how I used it. Again, here I differentiate this guy first, but book introduced the second one. It doesn't matter. Any question now? Yes. Like this one here? Like what? Right side above equal sign. This one to that one? Yeah. Do you recognize this is your f of x? That's your g of x? That part's okay? Okay. Now, this is f prime of x, right? It's a derivative of that vector, and that's g of x. So I hope you see that that's a product rule. F prime of x times g of x, right? Okay. So here, that's your f of x. Nothing happened to that f of x here. And that is this g of x differentiated alone. So that's g prime of x. How about that? Yeah. So f of x times g of x is f prime of x times g of x plus f of x times g prime of x. So that's how the product rule is applied. Fair enough? Any other question? Exercise number 4. What is that? Evaluating the derivative of x equals pi over 2, right? Here is another notation I'd like to introduce, very useful. Here, f of x is not here at first. I didn't call this one f of x and g of x, right? The functions are there without names, right? So we keep going like that without names. So following notation is useful. So d dx of this was the original problem, 5x squared times the sine of x, right? Like that. That's a derivative, right? Now in your head, you think about, I'm going to apply the product rule, get the derivative out. Then what is the next thing we're about to do? We're going to plug in x equal pi over 2 to that formula, right? And they wanted to write it here, create a notation. So this is what they did. Put the big vertical line out there that covers the entire thing. As a subscript, you write down x equals 2, not pi over 2. Then whole trained mathematicians knows that, oh, here's the order of operation. First, consider the product of these two functions, then differentiate it using the product rule, and you calculate all that thing. At the very end, you plug in x equals pi over 2, right? In my opinion, if you change that to bracket, it is also not highly standard, but to some mathematicians, a standard notation. It just clarifies a whole lot. So you put that bracket around it as a subscript to write down x equals pi over 2, then people, oh, he wants to, at the very end, he wants to put x equals pi over 2 in there, right? Now, do you see that it's going to be a number eventually, right? Now, let me ask you this question. Before we go into this technical part, What does this whole thing mean? You plug in pi over 2, you get a number out of it. What does that number mean? In physics, it means velocity. In geometry, it means in geometry, not analysis. In xy plane, what does this mean? Slope of a tangent line, right? Velocity and slope of a tangent line, right? Let's not forget that. That's the meaning out there in the world. Right now, exercise number 4 is this big clunky notation introduced to you with a big question mark in there. What is it? Go for it. All right, how is it? It's order of operation. You look at this big notation. One thing that, wow, there's too many things written in one place like that. One thing you have to understand is that what is the order of operation going on here? This really helps you. Whenever you look at a complicated mathematical symbols, first thing you have to attack is what is the order of operation there? What is the first thing you do? You first consider this 5x squared times sine x. Next thing, differentiate, right? And simplify, and then plug in x equals pi over 2. You have to go through that procedure. But it was already done. What is the derivative of this guy? Already calculated there, right? So I substitute it there and plug in x equals pi over 2. Question? Yes. No, this is has to be in radian. That's when we're saying function in mathematics, it means it's a function of real numbers, and it has to be in radian. That is not going to be specified, and it's something that you're responsible for. But thanks for the question. It has to be clarified here for you before the test. Anything else? Make sense? All right. All right. It is kind of telling you what we have just done means the following. If you sketch the graph of 5x squared sine x, right? And so the graph and what we had just calculated is a slope of this line there. So I'm going to also copy that. It's a good reminder. That's what it is. What's the slope there? Anybody remember the slope? Slope m equals 5 pi. That's right. That's what we just calculated. All right. This next tackle. It's getting harder. Not complicated. You have to think about it a little bit. How about this y prime? In the context, how do you understand y prime? This is a derivative, right? Yeah, derivative. But there's no f of x in here, right? What is a good notation to clarify what this means is d dx notation, right? So you dy, y is defined like that, and down there dx indicating x is our main variable. It could be dy dt, it could be dy ds, it could be dy dz, right? Depending on what letter you use. Fair enough? All right. What's the problem here? By looking at this function, it's a product of how many functions? Three functions, right? So it really helps. I don't know how to do this right away. In that case, let me go back in here. If you don't know how to differentiate your grouping, I grouped that into two factors. I didn't group it as a 5 times x squared times sine x. I grouped it into two, right? Now what I did here is that I didn't calculate it because I didn't know. I pretend I didn't know, and I put that place in there. This is going to be the place of derivative of 5x squared. Not in your mind, but I wrote it down with the proper notation. That really helps, right? So here is the situation. Now you are asked to group this one into two functions. There are two ways to do that, three ways to do that, right? Right? It's up to you. The answer is going to be the same. If you're applying the product rule, you don't know the derivative in place, use that ddx notation and take care of it later. Makes a big difference. All right? Go for it. This is going to be exercise 5. So this is my first level of thought, first level of applying product rule. Does that make sense? You look at this whole thing as a derivative of one function, and when I'm about to differentiate it, no idea what's going to be. So I just copied what I have in mind. This is supposed to be the place of derivative of x to the third times ln x. Don't know the answer? I wrote it down, this notation, right? And this is your g of x. Now it's f of x. Now I know the derivative of cosine, right? That's negative sine x. So I don't have to put d dx in there. I just write down the answer right away. Make sense? Yeah. And when I'm doing that, I put the parentheses and dot symbol, and that's the right thing to do, right? Please consider using, don't write it like times negative sine x. It's understandable, but it's a terrible notation, right? If there's a negative symbol, you have to surround it with a parenthesis, especially like this. All right, that's not the answer, is it? You have to take care of this guy, right? So go ahead and carrying out this one would be bulky. Keep repeating the same thing. And so I would go ahead and start another. If there's one bullet item, that's where we're going to come back. And you want to take care of this one, right? What is the answer to that one? So you start here like this again, but write this one down and see if you can answer this one. Once you figure this one out, come back in here and replace that. So let me label this one. It's actually item number 1. We want to come back. Right now, I neatly organize our thought here, but I still need to take care of this one. So item number 2 says that, all right, I'm going to write that down so that you remember what you're doing and the reader knows what you're doing in the second stage. So I'm going to take care of this guy here, d dx of x cubed times ln x. What is it? You calculate that using product rule again, then come back in and fill in. All right. Since we're running out of time, let me just do that here. What is the derivative of this one? 3 times x squared. Is that right? Ln x, that's a product rule. Differentiated, not differentiated. Now x cubed is going to be there, right? How about this one? Everybody knew the derivative of ln of 17 incorrectly, right? Now this time, what is the correct answer? 1 over x. That's the correct answer, right? So that one is be 3x squared ln x, right? Plus, these do cancel, right? Giving you x squared. Fair enough? This entire thing should replace that one in there. So final answer is that with the parentheses, this is repeated 3x squared times ln x, right? Plus x squared. This whole thing multiplied by cosine x and minus, I can pull that out, and x cubed times ln x times sine x. And then you can even expand that cosine x there, right? Are you excited about finding the second derivative? Nobody is excited about finding the second derivative. What we just calculated is a first derivative, right? But physicists got to calculate a second derivative, right? You're staring at it that, man, I'm going to call it a day. We're going home.